TNPSC Combined Statistics Services exam. Today we are discussing about scaling and De Morgan's law. Scaling comes under the topic of classification of variables, and De Morgan's law is associated with the probability. Scaling. When one hears the term measurement, they may think in terms of measuring the length of something, that is, the length of a piece of wood, or measuring a quantity of something like a cup of flour. This represents a limited use of the term measurement. In statistics, the term measurement is used more broadly and is more appropriately termed as scales of measurement. Scales of measurement refers to ways in which variables or numbers are defined and categorized. Each scale of measurement has certain properties which in turn determines the appropriateness for use of certain statistical analysis. The four scales of measurement are nominal, ordinal, interval, and ratio. Let us discuss this in detail. Nominal. Categorical data and numbers that are simply used as identifiers or names represent a nominal scale of measurement. It is a type of data that is used to label variables without providing any quantitative value. For example, you might classify the control group as group 1 and the experimental group as group 2. These classes are mutually exclusive and collectively exhaustive. Your social security number is another example of nominal data. Calculating averages and ranking them has no meaning in this kind of cases, but modes and frequencies can be calculated. Ordinal. An ordinal scale of measurement represents an ordered series of relationship or rank order. Individuals competing in a contest who achieved first, second, or third place represent ordinal data. Thus, ordinal scales indicate relative position but not the magnitude of the difference between the objects. The object ranked first has more of the characteristic as compared with the object ranked second. But whether the object ranked second is a close second or a poor second is not known. In marketing research, ordinal scales are used to measure relative attitudes, opinions, perceptions, and preferences. Measurements of this type include greater than or lesser than judgments from the respondents. Common examples of ordinal scales include quality rankings like chili is hot or hotter or the hottest. Interval. A scale which represents quantity and has equal units but for which 0 represents simply an additional point of measurement is an interval scale. The Fahrenheit scale is a clear example of the interval scale of measurement. Thus, 60 degree Fahrenheit or minus 10 degrees Fahrenheit are interval data. Measurement of sea level is another example of an interval scale. With each of these scales, there is direct measurable quantity with equality of units. In addition, 0 does not represent the absolute lowest value. Rather, it is a point on the scale with numbers below and above it. In those scales, 0 degree Fahrenheit and 0 degree Celsius does not indicate the absence of temperature. Ratio. The ratio scale of measurement is similar to the interval scale in that it also represents quantity and has equality of events. However, this scale also has an absolute 0. No numbers below 0 exist. The absolute 0 refers to the complete absence of the characteristic being measured. Very often, physical measures will represent ratio data. For example, height and weight. If one is measuring the length of a piece of wood in centimeters, there is quantity, equal units, and that measure cannot go below 0 centimeters. a negative length is not possible. Similarly, a person weighing 100 pounds is two-thirds as heavy as a person who weighs 150 pounds. Let us try to understand what we have learned by looking at this table. Here, nominal data just indicates the difference, but the ordinal data indicates the difference, and also it gives us an idea about the direction of the difference. And interval scale of measurement indicates difference, direction of difference, and it gives us an idea about the amount of difference. And the ratio scale of measurement, it indicates difference, direction of difference, amount of the difference, and it has an absolute zero too. Now let us have a look at this picture. Here we can see that nominal data are just named variables, but ordinal data are named variables which are ordered variables. And interval scale of measurement are named, ordered, and are proportionate interval between variables. And when it comes to ratio, they are named, ordered, and has proportionate interval between variables. Also, they can accommodate absolute zero. Now let us see certain examples. Our first example is student IQ ratings. It is an example of interval scale of measurement because IQ ratings never take absolute zero value, and the difference between two values has a meaning. Thus, it belongs to interval level of measurement. The second example is distance students travel to class. The answer is ratio because the distance can take the value absolute zero. And the third example is the jersey numbers of a soccer team. The answer is ordinal, that is, it belongs to ordinal scale of measurement because jersey numbers are numerical values and it can be arranged in an order, but the difference between two values has no meaning. And our next example is a student's state of birth. It is a nominal data because state of birth can only be named. It cannot be arranged in any manner that gives a meaning. Our next example is a student's academic class, that is, whether he is a freshman or sophomore, junior or senior. It is an ordinal data because we can list the academic classes and it is possible to arrange them in order of grade, but the difference between two values has no meaning. Thus, the variable is of ordinal level of measurement. Our next example is number of hours students study per week. The answer is ratio. It is because these values takes numerical values and an absolute zero is possible. Thus, it belongs to ratio level of measurement. Our next topic is De Morgan's law, and this is a topic related to probability. De Morgan's law states that the complement of the union of two sets is the intersection of their complements, and the complement of the intersection of two sets is the union of their complements. These are mentioned after the great mathematician De Morgan. This law can be expressed as A union B the whole complement is equal to A complement intersection B complement. In set theory, these laws relate the intersection and union of sets by complements. Note: a power set includes all the sets of a given set including the empty set. The power set is denoted by the notation P of S, and the number of elements of the power set is given by 2 raised to n. All the elements of the power set are sets. This is an additional point to be added to the topics of probability.